Hi, welcome to CHEM100. As we're going through these videos and as you're learning the material, I recommend that you have a printed copy of the lecture packet available and that you fill out the notes and do the practice problems. Stay engaged while you're watching the videos. Let's get started. The first thing we need to go over are the three states of matter. So solid, liquid, and gas. And after the word solid, you see a lowercase s in parentheses. And as we start talking about how to write formulas and equations, you're going to see this notation a lot. So that is the abbreviation for solid. And it tells us that the compound is in the solid form. And then a lowercase l in parentheses for liquid, and a lowercase g in parentheses designates a gas. Let's talk about the properties of solid, liquid, and gas. So first off, do they need a container? And that gives us insight into the shape of the state of matter. So for solids, most of us would say no. They do just fine without a container. And that's because they have a well-defined shape. For instance, the pen that I'm writing with, the plastic part of it at least is a solid, right? And I don't need to put it into a container, and I don't expect the shape of the pen to change. Liquids, yes, they need a container, and that's because they have an indefinite shape. Or it's related to the fact that it has an indefinite shape. The shape will change and conform to the container. And same thing with the gas. The gas is going to expand, and it's even more extreme than what we see with a liquid. The liquid, like if you think about a water bottle, the water inside the water bottle will go to the bottom of the container and take on the shape of the bottom of the container. But the gas molecules will actually spread apart and fill up the entire container. And that begs our next question here. What can we say about volume? For a solid, we expect constant volume. And what is volume, right? Volume is the amount of space that something takes up. So again, with the pen example, I always expect this pen to take up the same amount of space in my bag or whatnot. It's not going to grow bigger or grow smaller. And the same thing with water. If you have a constant amount of water, it's going to take up a constant volume. And I know some of you are thinking ahead, but what if you increase temperature? Yes, things will change at different temperatures. I'm kind of assuming here that we're just at room temperature and not messing with the temperature. The one that's interesting is gases, right? Gases do not have a constant volume. And that's because they expand to fill the container, as we see in this picture up here. So the volume of the gas is going to be the volume of the container. Next thing we want to consider is the level of organization of the particles. Solids, the particles, the molecules, the atoms, they're very organized. And they're also packed really close together. I think it goes hand in hand. If we think about travel and when you're packing a suitcase, right? If you want to fit a lot of clothes and whatnot into the suitcase, it helps to be very organized because then you can maximize the packing, the number of particles or clothes that you fit into that area. Gases, on the other hand, one of the things about gases is they have minimal interaction between particles. And let me make note of that. That's important to know. Because the organization that we see with solids is due to the interactions, whether they be bonds or intermolecular forces, but it's due to interactions between the particles. With gases, we have minimal interaction between the particles. And that is related to the fact that if you just look at gases and you had the ability to see the particles, it would look really disorganized. The liquid is somewhere in between, right? It's not as crazy as a gas, but there is some fluidity, and as you can see even from the picture up here, it's not super organized, kind of like if you packed in a hurry. But the particles are still pretty close together in the liquid state. And that goes back to the fact that we have a constant volume. And then with gases, the particles are not close together. There's minimal interaction. They're going to spread out to fill up that container. The one exception, though, that I want to make note of, especially as we enter the summer season here and people will be barbecuing and all that, at high pressure, like in a propane tank, we can force those molecules to be close together. So the exception, so in general, no. The exception is at high pressure when the particles are close together. And again, if I had to illustrate that or give you an example, a helium tank, a propane tank, you're taking it and you're putting everything in there under high pressure and keeping everything, even in a soda, right? I don't mean to digress here, but even in a soda bottle, a closed soda, you have carbon dioxide, which is a gas. And they're pretty close together as long as the soda cap is closed and it hasn't been opened. Alrighty, for this next part here, one of the main objectives of this first lecture packet is for students to be able to distinguish between chemical properties or chemical changes and physical properties. So let's start by defining those terms. So a physical property can be observed and measured without changing the structure or identity of the substance. On the flip side, a chemical property involves bond breaking and bond forming. So we're going to do plenty of hopefully fun examples here to kind of practice this. What is an atom? So an atom is an individual element. What is an element? Well, for now, you're going to be able to identify atoms or elements using your periodic table. So if it's listed here on your periodic table, then it's considered an atom. So for example, helium or carbon. So individual elements, they consist of a nucleus and protons, electrons. We're going to go into all the details later. But for now, you need to know that an atom is an individual element. We, as chemists, use models to represent these elements. And so individual spheres would represent atoms. And we're going to see some pictures too. So it's not just the molecular modeling kit that you have to kind of be able to interpret. You also want to be able to interpret two-dimensional drawings where they look like spheres or circles. That's in contrast to compounds. So once you start connecting the atoms and you build something a little bit more complicated. So here, this is a water molecule. The red sphere represents the oxygen, and then these little sticks, this is the bonds. And so sometimes they're lines, sometimes they're sticks, sometimes people just draw them jammed together, and that's acceptable too. But when you start connecting things, connecting the atoms, that's considered to be a compound. So for a definition, a compound is two or more atoms. And they're connected. And examples: water, oxygen gas like O2. We're going to go into more detail about that. I just want you to start thinking about how we're going to represent these things. It's going to help us understand the difference between chemical and physical changes. So in problem number 1 here, we're asked to classify each of the following properties as being chemical or physical. First, let's consider color. So 2 pieces of material. One is like neon yellow and the other one is blue. It's got a pattern on it. I can observe the color of these pieces of material without altering the structure or changing anything about the material. Because of that, you can classify color as a physical property. Remember, physical means it's the same thing at the end of the day. In letter B, we're looking at melting point. So melting point is a technique that chemists use to characterize solids. Every solid has its unique melting point. And what is melting point? You're observing a phase change. So it's going from a solid to a liquid. Phase changes are always physical. So why are phase changes physical? Let's look at melting point specifically. So what we have here are a bunch of water molecules, and they're relatively organized because they're currently in their solid form. As they transition and start melting and become liquid, the only thing that's going to change is that they're going to start moving a little bit faster and become a little bit more disorganized. And actually, when water melts, it's one of the weird ones. It actually takes up less space in liquid form, but they just move around more, right? They're still water molecules. I didn't have to break them apart. And so whether we're looking at the solid or the liquid, we're still looking at a water molecule. How do scientists test flammability? Well, in order to test flammability, you need to burn whatever you're curious about. So let's look at the fabric from earlier. If I try to light the blue fabric on fire, well, it's pretty successful there and it's burning. It's creating kind of like a black, plasticky kind of smoke. And I could record my observations about the flammability of the blue material. Could do the same for the neon yellow material. However, after I burn this material, start a fire in my house, right? After I burn this material, there's no way that I'm getting it back. So I broke the bonds within the fabric and created some kind of new materials. So for instance, when I was burning the blue fabric, you might have saw that smoke coming off of it. So that was a new compound or molecule that was created as a result of me burning the fabric. So by definition, a chemical change involves bond breaking, which occurred with the material, and the formation of new bonds. So we'll classify flammability as being a chemical change. We can make a similar argument for toxicity. How would you test toxicity? Well, you'd have to eat something or feed it to a lab rat or something like that. We need to see how the body metabolizes whatever we're curious about. At the end of the day, though, it's not going to be the same compound or same food that you started with, right? The body's going to break those bonds and change them into something else. So this is also going to be chemical, because testing it requires a chemical change. Hardness. Now, when I want to test hardness, we can just maybe scrape something, see is this material hard or not? But I haven't broken any bonds. I know it looks like, oh, you just damaged a piece of wood here, but yeah, maybe I scratched it a little bit, maybe I damaged it, but it's still the same thing, right? It's different from if I had burned it, it wouldn't look anything like wood. Here, even if I scratch the whole thing up, it's still wood. So hardness is physical. Or if you test a rock, right, and you somehow scratch it with a piece of diamond, it's still the same rock, it's still the same piece of granite or sedimentary rock or whatever you're testing. You didn't change the identity of that substance when you were testing the hardness. Density will be the last example here. Density is the amount of stuff that fits into a given space. It's often confused with something being heavy or not. Styrofoam packing material is very low in density, but if you take a similar object, maybe a rock that's the same size, it's a lot heavier because there's more atoms and molecules packed into that space. So the density of the rock is much greater than the density of styrofoam. We measure density by getting mass and volume information. Both of these things don't damage the rocks or the styrofoam, or whatever we're interested in, the liquids. There's no damage or change in identity of the substance. So we're going to classify density as being a physical property. Moving on, what is the primary difference between chemical changes and physical changes? Chemical changes, chemical properties, kind of just lump them all together. Things that are chemical in nature are very difficult to reverse, if not impossible. So when I was burning the fabric, that's it, right? The fabric's burnt. There's no way to reverse it. However, and get it back to perfect fabric. However, if you're melting an ice cube, well, you could take the ice cube out of the freezer, melt it, you could throw it back in the freezer, get it to be a solid again. So physical changes or physical properties are easy to reverse. I mean, I'm going to put easy in quotes. It requires, maybe some change in conditions, but you can imagine doing it. So this is kind of a good, set of hints if you're trying to distinguish between the two things, chemical or physical. Alrighty, let's go over your answers to number 2, where you were asked to characterize each process as being chemical or physical. So making ice cubes, hopefully everyone recognized that as a phase change and classified it as physical. Burning natural gas. So to start introducing some terminology here. Whenever we burn something, that's known as a combustion reaction. Combustion means to burn. Combustion is always chemical in nature. All right, in letter C here, you can imagine having a brand new piece of silver jewelry, really shiny, very beautiful. Over time, it'll start interacting with the oxygen in the air, and it's going to form a brand new compound. That compound is silver oxide, and it's a totally different color. It's like gray/black, kind of looks a little bit ugly, and so that's what they mean by silver jewelry tarnishing. Don't worry too much about the equation. Later on in the course, we're going to learn how to write equations. I just wanted to start introducing some of the concepts here. This is known as a redox reaction. It's actually super common. Substitute out iron for the silver. You have iron with oxygen forming iron oxide. That's rusting. Iron oxide is rust. So can we classify this as being chemical or physical? I know this has always caused confusion because people say, well, I can fix my jewelry. I can get one of those cloths and rub off the tarnish, or I could bring it to the jeweler and they take care of it. They're not reversing the process though. When you get your jewelry cleaned, it's the same thing you do with rust, right? You take some sandpaper and you'd actually remove the rust until you get to a layer of iron that's brand new. And so it's the same thing with the jewelry. They're just removing the outer layer, and that's how they clean it. So since you formed a brand new compound when something tarnishes, we're going to classify this as chemical. And yes, if you keep on, cleaning your jewelry over time, you're going to have less and less jewelry. The mass of the silver will decrease. Alrighty, in letter D, photosynthesis. If you're not familiar with biology yet, that's fine. So what occurs in photosynthesis? The plant takes carbon dioxide and water and turns it into sugar and oxygen using the energy from the sun. We have some compounds over here that are not the same as the compounds over here. So bonds have been broken and bonds have been formed. And so we'll classify photosynthesis as being chemical. Making bread, hopefully you also classified that as chemical. Just thinking about what we discussed earlier. You can't reverse it, right? Once you put the eggs and the flour and the yeast in there, good luck getting it back to yeast or flour. It's an irreversible process, which gives us an indication that it's chemical in nature. Letter F is a tricky one. Dissolving sodium chloride or just, table salt, if you take some salt and you mix it with water. Personally, I've always classified this as a physical change because I think about like desalination. I know that I can take the salt water and boil the water off and get the salt back. I have heard arguments that it's chemical, so it wouldn't be a test question. It's just a good discussion question. Either or, you could go either way. And people are classifying it as chemical because they said, well, when you dissolve the sodium chloride, the sodium separates from the chloride. And that's why there's the argument that it's also chemical in nature. Personally, I go with physical because I know that I can reverse it. Condensation of water, well, that's just a phase change. You're taking water vapor and it's forming those little droplets. So we know that all phase changes, without a doubt, are going to be physical. And then same thing with the orange juice, right? It's going to be physical because even though I'm adding water, I'm not changing anything about the orange juice. I'm not like breaking the bonds, just mixing it up with something else. So in my mind, the formation of a mixture of things, you take a bunch of different ingredients, you're not cooking them or anything, you're just combining them and mixing them up, is usually physical because we can reverse that process. We can imagine taking the water out of the orange juice at some point. So for question 3 on the top of page 3, on the left-hand side, we see an image of tightly packed, super organized molecules. After that, we see a reaction arrow, and the picture on the right-hand side shows the molecules pretty disorganized, and now they're spread pretty far apart. So what's happened here? So on the left-hand side, based on the level of organization and the packing, it's safe to assume that we're looking at a solid. Over here, since the molecules are more spread out and relatively disorganized, I'm going to classify this as a gas. Now, based off of the colors in the image, we have a black center atom surrounded with two or connected to two red atoms. I know that that's how we build carbon dioxide or CO2. Carbon dioxide in its solid form is known as dry ice. Dry ice is super cool because it doesn't melt. It skips the liquid phase entirely and turns directly into a gas. It's still a phase change, and this phase change is known as sublimation. Because it's a phase change, we can safely classify this process as being physical. However, even if you didn't know that it was dry ice, you can still see in the two images that the connectivity, the way the atoms are connected, remains the same. One black with two reds. And since no bonds were broken, it's physical in nature. Alrighty, let's look at question 4 on page 3. In image A, we see some tightly packed diatomic molecules. They are composed of two different colors, red and green. So we know that they're made up of two different elements. We're not given information about what elements, but it's two different elements. On image B, or in beaker B, the molecules are connected to the light colors. So green is with green and red is with red. What does this mean? This means that the molecules in the first beaker had to have broken and reformed new molecules to get the light color with the light color. So whenever we see bond breaking and bond forming, that's a good indication, or that's the main indication that it's a chemical change. Something very similar is going on with A to C. The molecules start out as diatomic, and then bonds must have been broken to have obtained the single elements or monoatomic elements that we see in image C. So I'm going to classify this as chemical. Granted, there wasn't the formation of new bonds, but since bond breaking occurred, it's a chemical change. In our last example here, A to D, we start out with the same tightly packed diatomic molecules. We have a red sphere connected to a green sphere. And then when we look at image D, it's still red connected to green, but now they have spread further apart. And that's a great clue that we're looking at some kind of phase change or a physical change. In summary, we can say that A to B is chemical, A to C is chemical, because in both of these examples, bonds have been broken. And then for A to D, we're looking at a phase change, which is physical.